Okay, yeah. Hello everyone, I'm Jonas Gebele, PhD student at TUM, and I'm gonna talk about blockchain-based prediction markets. So, well, the short explanation.
I will shamelessly present the recent addition to Ultrabit website called ZK Catalog that my talk will refer to. So I realize that this audience might not be the most Ethereum centered audience. So if you don't know, Ultrabit is a website that basically contains a lot of technical information about state of L2s and the general state of Ethereum ecosystem. So I will start by giving a gentle introduction to ZK, but first to maybe get a better feeling of the audience. So some hands up. There will be some terms, and you just raise your hand if you know what they are. So who here knows what ZK is? Okay, nice. Who of you know what an L2-centric roadmap is in the context of Ethereum? Okay, good. Who knows what a trusted setup is? Okay. Who knows what elliptic curve pairings are? Okay. Maybe somebody here knows about Fiat-Schmidt transformation? Good. And maybe anybody knows about the Frey soundness conjecture? Okay, nice. Maybe I was looking for somebody to talk about this, so maybe we should also catch up after my talk. But nice. I see, it's nice. I will maybe give some introduction as well, and I will start very basic. So I want to talk about ZK. So in zero-knowledge setups, you always have a prover and a verifier. And what is important is that the interaction should always start with the step 0, where they agree on some setup params, and these setup parameters could be things like cryptographic field or elliptic curves that they decide to use, but also trusted setup. And maybe most importantly, they should agree on a program that they will be kind of proving and verifying. So this is crucial, that the prover and the verifier has the same view of this program. And then they engage in this protocol where the prover can prove the execution of this program on some input parameters, some possibly being public, some possibly being private, known only to the prover. And the verifier can check that this program was correctly run on this on the public, based on public information. And the reason why ZK proofs are important in the Ethereum ecosystem context is that usually this program that you see here is a state transition function of some blockchain, like Ethereum L1 or some L2. Prover proves the correct execution of blocks, and the verifier is usually some sort of smart contract, like it could be a rollup smart contract or maybe a bridge. And in this way, you can kind of concisely compress the computation of some L2. Now I want to say a couple of words about trusted setups. So this is a procedure that has to be run before, and it generates some public data for the prover needed for the prover and for the verifier. And the word trusted means that this setup also produces some sort of toxic waste. So this is cryptographic secret data that shouldn't be known by anyone, and it must be destroyed. And if it's not destroyed and available to somebody, then this person can forge arbitrary proofs, and kind of the whole model breaks down. So this is kind of a problem. And if you want to have a bit more background on the trusted setup, I have prepared this write-up on our forum, or you can go have a look. We also propose a framework for thinking about trusted setups. Feel free to check our forum. Now, one final thing I wanted to say before going in depth is recursive proving, which I think is nicely summed up by this meme. So basically, recursive proving is a construction. Do I actually point it? No. Recursive proving is a construction where this program that is proven and verified is a program that verifies another zero-knowledge proof. So when you generate a proof of execution of this program, you quite literally verify the verification process of a zero-knowledge proof. This is kind of recursion type of thing, and It has a couple of use cases currently in production. The first one is you can, for example, prove several L2 blocks or blockchain blocks independently, and then recursively join these individual proofs. So then you will be kind of checking the proofs for each individual blocks within another proof. This is one use case. Another use case is, for example, you can use a fast ZK proving systems that produces huge proofs, and but you don't want to pose this and process this on chain. So you verify this proof with another proving system that produces very short, very efficient proofs, and this one goes on chain. And if you have a look at the ZK catalog, this, for example, is an entry for Bootjump from MetaLabs, ZK Sync. They have exactly this setup where they have a ZK VM and final wrap. So this is represented by these two entries. Okay, so I want to focus now on the present of proving systems. A little caveat is that it's L2-bit perspective, and this means that we're interested in proving systems that are deployed on Ethereum in production and that secure some value. This is what we kind of try to watch. But I will also try to give a bit of a broader perspective as well. But this is a very, very huge field, so yeah, I just cannot cover everything in my 25-minute talk. Okay, so I will talk about an average project, and this is like an average project that uses some ZK. Usually it's like a L2 or a bridge, and maybe I will just say what you should expect kind of this average project to use, and there are quite many of these average projects. So first of all, your average project will probably use a ZK VM. So this is this type of construction where you have basically a virtual machine, and a proving systems proves the correct execution of some program within this virtual machine. Usually this virtual machine will be running on RISC-V architecture, because in this way you can compile from Rust, but not necessarily. Some virtual machines have some customly defined instruction sets. And here is a screenshot again from ZK catalog where you can see this ISA thing for different proving systems. We track it. So in addition to this ZK VM, this average project will most likely also have this final wrap that I described earlier. So it will take a proof generated by ZK VM and reprove it with a snark for efficient on-chain verification. So here you can see a screenshot for SP1, which uses this exact architecture. And probably this final wrap will be a Plonk proving system implemented by Gnark library from Consensus, but it could also be a Groth16 snark. So you can see SP1 allows using both Plonk and Groth16. So next, this average project will be, if it's using this final wrap, then it needs some sort of trusted setup. Most likely it will be using Aztec Ignition trusted setup that was run in 2019. It's quite a good trusted setup. It could also happen that the project decides to run its own trusted setup, but then most likely it will be worse than Aztec Ignition in terms of participants and public participation. So next thing to say about the average project is that most likely its proving system will be a couple of times slower than the cutting edge research. And it's not because these guys are slow or stupid or don't know what they're doing, but just because the current development of technology evolves just too fast. So for reference, there is this website, ithproofs, that benchmarks different modern ZK VMs. And I had a look at all the ZK VMs in the pipeline that are not yet used in production, and I found out that basically most of them, 21 out of 26, are not used, and only 5 are currently deployed. So this gives you a feeling of the gap between the most modern thing that is available and the things that are running in production. And then finally, this average project will not, most likely, will not allow any random person to come and submit a proof on chain, just because nobody really trusts the proving systems that much. So they expect there are some exploits, there are some bugs. So most likely, either proof submission, or if it's L2, block sequencing will be centralized. So it will not be possible for anybody to just come up with a proof and submit with some important on-chain consequences. Okay, so maybe this was the average thing. I wanted to call out a couple of projects that maybe deviate notably from this, sometimes for the good, sometimes for the bad. And I want to start with the Starknet's Starkware Stone. So this is the only project that does not require trusted setup because they post the Stark proof on chain, and I think they deserve a round of applause for this. That's the only one. Maybe to counter this with something bad, I have a call out for SP1 Growth 16 final wrap. I mean, SP1 is a great project, but in particular, the Growth 16 final wrap has a trusted setup that was run by 7 people, all affiliated with a succinct team. So this is not a way to do trusted setups, and let's hope that something will change sooner rather than later. But interestingly enough, there are some actual projects like Gnosis Breach, Facet L2, and Zircuit L2 that are using this in production right now. So you can see this information on our ZK catalog as well. I call out to Linea for implementing ZK EVM without implementing ZK VM. This is a nice construction where they have a lot of snark circuits. Interestingly enough, in the process, they managed to use 3 different trusted setups for 3 different elliptic curves. That's quite a construction. So next call out goes to Risk Zero, their Growth 16 final wrap. They also had to run their own trusted setup ceremony, and this is an example of a good trusted setup ceremony. It was quite public, 238 different participants. Yeah, it's a big green thumbs up from us. And the final call out goes to Tyco. So Tyco L2 is a layer 2 that runs a multi-prover setup, which means they prove the blocks both with SP1 and Risk Zero provers. I mean, they also use TEs actually as a third source of independent proving. So this type of setup increases robustness. Unfortunately, they still have not fully committed to this, so they're not proving all the blocks with all 3 different methods at the moment. But this is a nice step towards decentralizing proof systems as well and making it a bit more robust. So next, I want to say a couple of words about the security.
May I have a question?
Yeah.
The thing is, your caller, for instance, for Linea,
Mm-hmm.
I mean, Joseph Rubin's behind it, and he should know how to do it. What do you think? Why is he doing it? From your point of view, not that good?
Mm-hmm. I mean, so this, for Linea, I would not say that the call-out is something bad. It's just an interesting setup that I wanted to highlight. The reason why they're doing it like this is because they started doing it quite a while ago, when the more maybe modern and efficient constructions like Risk Zero, SP1, ZK VMs basically were not, let's say, mainstream. So when they started building this was the only way to do this, like actually proving EVM within circuits, and they developed this snark circuits for this. But they are also facing a lot of challenges now because every time EVM is updated with a new precompile, with a new change, they have to also modify the circuits, and it's quite complicated. So yeah, I wanted to now point out a couple of security concerns that we see, and maybe the most conceptual thing that I want to say is that ZK technology is getting much more adopted now, but still many users, many developers think of it as a black box that somehow should work. And I think this is kind of a dangerous approach, and we have to be much more nuanced than that. And that's why I think it's important to kind of educate people and to talk about these things. And this is maybe a scenario for you to think about. So imagine you have your $1 billion lying around, and you want to put it in a smart contract locked by ZK, and it should be unlockable only by you. So maybe this ZK program maybe verifies a signature with some computation over your DNA. It's not so important. But the important bit is that once somebody presents a valid zero-knowledge proof, the money is withdrawn, and that's kind of it. So the question is, what should you check before doing this? Because 1 billion is a big sum. If you think it sounds a bit arbitrary, this is kind of the scenario that many blockchains are facing now, like Arbitrum, Base, are big blockchains. Maybe they're considering moving to ZK. So what should they be mindful about? So the concern number 0 should always be bugs, because this technology is just too immature. There are many bugs floating around. I think there is no arguing about that. There are a lot of audits and formal verifications that find issues all the time. But in reality, as I said, proof submissions is not decentralized, so it's not battle tested yet. There might still be many bugs around. Maybe the next thing that would be easier for you to check is which exact program is being proven. So as I told you in the beginning, it's very important that the prover and the verifier have the same common view of what program is being executed. So imagine a scenario, you maybe outsource the deployment of this smart contract to somebody, and they are malicious. So they add this simple check to your program. So if a proof is submitted by a hacker, then the proof is considered to be valid. So they later can come and steal your $1 billion. And the solution here on your side should be that you have to compile the ZK program from the sources, making sure that the sources are correct. And usually this gives you some sort of a hash commitment to ZK program that prove and verifier are running. And the keywords here are program hash, verification key hash, and so on. And I want to say that this is something we're also trying to put on L2Bit to give a bit more visibility. But this is, so here on the left you can see this verifiers column that is already live on the ZK catalog, but also these types of hashes, program hashes, commitments, you can already observe on chain for different proving systems. So you kind of always have to compile yourself from the sources and check that the commitments that you get is the same commitment that is present on chain. So the second concern that I want to highlight are the bits of security. This is the question of how much brute force is needed to basically mine a valid proof for your verifier. And this is a very complicated topic. There are the current provers used in production use different different values for this. So for example, Stone from Starkware targets 80 bits of security, SP1 from Succinct targets 100 bits of security, Linear, Zisk, Polygon, ZKVM target 128. So already by choosing a proving system that you're using, you have this implicit security parameters that come with it. And here I want to say that most ZKVMs estimate bits of security based on an unproven conjecture, basically Frey soundness conjecture. And Ethereum Foundation announced a bounty of $1 million, making it a $1 million problem to solve this, prove this conjecture. And the final thing I wanted to highlight is the trusted setup. So can all the participants of a trusted setup gang up on you and steal your $1 billion? So probably for at-stake ignition, it's not going to happen. For SP1 growth 16, this maybe could happen, I don't know. But this is something we also try to highlight and monitor on ZK catalog at the moment. So I still wanted to say a couple of words about the future. And maybe the most important thing to say is that we have this mantra in, Ethereum ecosystem, I hear it a lot, that ZK is the future, and there are many good reasons to consider it to be. So ZK enables fast, trustless bridges between different ecosystems. So for example, bridges between Polkadot and Solana from even our Bitcoin network is being connected on ZK. So this is very cool. Then there is this attempt by Ethereum Foundation to use ZK for scaling Ethereum. There will be a talk by Justin Drake right after mine, I believe. And here the idea is that validators will just verify zero knowledge proofs of the blocks, and then L1 can go as fast as you can prove blocks. There are also a couple of nice applications of ZK for privacy, both for cypherpunk users among us, but also for institutions who don't want to put all the internal operations in public on chain, but still want to prove that they are operating correctly, and so on and so on. So there are many applications. A couple of things that I expect in the future. ZK will become faster. There are all the time, there are some optimizations announced. A couple of things just from the top of my head when I was preparing the slides is this idea of implementing more linear multivariate polynomials instead of univariate in the spirit of sum check protocol. For example, Binias is doing this. There are some other attempts like use hardware acceleration, GPU parallelization, but there are more and more ways to make ZK even faster, and there is a lot of work being done. And finally, ZK is becoming more secure, so there are more audits going on, but also there are formal verification efforts. Basically, these are the mathematical proofs that the ZK implementation basically aligns with the specification. And this is a bit hard to do, but when it is done, then this provides quite a good base for trusting the systems. Also something to mention are these multi-prover setups where you generate 3 different proofs with 3 different proving systems. And it's unlikely that all of them have bugs. And here I want to highlight this incident that happened last week, actually. So there was a REST client of Ethereum that had a bug and stopped processing blocks for a couple of hours. But Ethereum continued to run because there were other clients producing and verifying blocks. So this is something we can also aim for in the ZK space, where if one ZK proving system has a bug, it's not affecting the whole liveness. And hopefully in the future we will see actual decentralized proof submission. So there will be possibility for hackers to actually exploit proof systems that are not that have bugs, and then we will have better understanding of which proof systems are secure and which are not. So that was it from my side. Thank you for listening. I have here a small list of talks that still will happen in the future about this topic. Feel free to check it out, but there are also some other relevant talks that I don't put in this list. So, yeah.
Thank you really much from our side. One question? Yeah?
Yeah, actually in the previous slide,